Chemical bond in general. Does anyone have an idea about what a chemical bond is? Anyone have a definition for me? No? Nothing? All right, well, this is what your book says. Okay, a chemical bond is a mutual attraction. A mutual attraction. What do you think it's between? Between, okay, yeah, between chemicals, between atoms. But it's between the nucleus of one element and electrons of another, or nuclei and valence electrons. Okay, so it's between the nuclei and valence electrons of different atoms. Okay, so let's think about the nucleus. What would be the charge of the nucleus? Positive. Why? Why positive? What's the nucleus contain? Protons and neutrons. Neutrons have no charge, right? So it's got to be a positively charged nucleus. Okay, what about electrons? Where are valence electrons located? The outer shell, okay? Valence electrons are the outer shell electrons, and they have what charge? Negative. Electrons have negative charges, okay? So this is what a bond is when two atoms are attracted to each other, negative part and positive part, okay? So we're going to look at two different types of bonds that will bring atoms together. The first of which is an ionic bond. Okay, an ionic bond. What types of atoms are ionic bonds between? Between what? Exactly, between a metal and a nonmetal. Some people also say these are between a cation and an anion. That's because cations are typically metals, anions are typically nonmetals. Okay, so it makes sense. This is the same thing. What's different about an ionic bond is that this is a bond where electrons are traded. Okay, they're given up. So atoms completely give up. They completely give up their electrons to another element. Everyone understands that this is how I write electrons, right? Everyone's got that by now? Okay, good. So atoms completely give up their electrons to another element. They just give them away, okay? And those other elements will take them. So that's what's distinct about an ionic bond. They give up electrons. They're not sharing them. They're giving them up. Okay? So opposite of that is what we call the covalent bond. Are we ready to change sides here? Okay. Opposite of that is called the covalent bond. Okay, covalent bonds are between what? Yeah, exactly. Between two nonmetals. Or two anions. All right, what's distinct about covalent bonds is that these are bonds in which atoms share electrons. Okay, so instead of one atom completely giving up their electrons to another, they share them. Okay, they get to split them between the two. And sometimes when elements share electrons, they share them unequally or not equally, okay? One atom wants electrons more than another. Do you remember what that term is called? Yeah, electronegativity. Okay, and we're going to introduce electronegativity a little bit more than we have thus far. Okay, any questions about ionic and covalent bonds? Covalent bonds share electrons. Ionic bonds give up electrons. All right, when we talk about electronegativity, I want you to have this scale in front of you, so I'll hand that out right now. When something is polar, that means there is an uneven distribution of electrons. They're not distributed equally. So an uneven distribution of electrons. Okay? So when something is polar, that means electrons are not shared equally. So we have something then called a polar covalent bond. Okay, so knowing what we know about these terms that make up this polar covalent bond, what can you tell me that's probably happening here? Yeah, Tommy.
A bond in which atoms are unevenly distributed.
Okay. Electrons are... Yep. Okay, so a polar covalent bond, that means two atoms are bonded together and electrons are favoring one atom over the other. Okay, so we'll say that this is bonded atoms have an unequal attraction for the shared electrons. So in a polar covalent bond, that means it's a bond between two nonmetals. They're sharing electrons, but one atom wants electrons more than the other, and electrons are shifting that way. Okay, so if you can picture that in your head, do you guys kind of see what I'm talking about here? If you can think about that in your head as having two atoms, having electrons between them, if it's a polar covalent bond, that means electrons are shifted one way or the other. Okay, and we're going to determine how they make that shift using our electronegativity values. Okay, before we get there, what do you think the term non-polar covalent bond means? That what? Yeah, exactly. Non-polar covalent bond means that they are evenly distributed. Electrons are evenly distributed between atoms. Okay, so on page 176, you can see kind of a visual representation of how we determine ionic polar covalent or nonpolar covalent bonds. Okay, and we're given a set of numbers for these. Okay, these numbers go along with our electronegativity scale or the Pauling scale that I gave you. Okay, so when we want to determine the electronegativity of a bond or the electronegativity value of a bond, we look at the two elements that the bond is taking place between, and we determine the difference in electronegativity of those two. Okay, so I'm going to tell you the rules here for these electronegativity values, and then we'll go back and do some work. Okay, so if the value is between 1.7 and 3.3, it's an ionic bond. If the values are between 0.3 and 1.7, it's a polar covalent bond. And if the values are between 0 and 0.3, it's a non-polar covalent bond. Okay, and these values are given on that little purple to blue to yellow to green or whatever chart on page 176. All right. So I wanted to take a look at these electronegativity values and how we determine what types of bonds they are if we're not exactly sure what we're looking at here. Okay? Does everyone have these values down? Okay. So let's look at a bond between hydrogen and sulfur. Okay, so just a bond that's been made between these two atoms. Okay, what we do here is we determine, first of all, the electronegativity values for each of these elements. Okay, so look on your Pauling scale. Tell me what the electronegativity value is for hydrogen. 2.2. And what's the electronegativity value for sulfur? 2.58. Okay, so what we do is we take bigger minus smaller. Okay, whatever it is, the larger one minus the smaller one. So we take 2.58 minus 2.2, and we get what? 0.38. In what range does this value fit? What type of bond would it then have to be?
Polar covalent.
Polar covalent. Okay, now let's look at what we know on the periodic table. Is hydrogen a metal or a nonmetal? Hydrogen's a nonmetal because it's a gas. Okay, it's a nonmetal. Sulfur is a metal or a nonmetal? Nonmetal. So you know it's got to be a covalent bond. You know it has to fit there. What about, which one of those is closer to fluorine, hydrogen or sulfur? Sulfur. That means sulfur is more electronegative, which means it will want the electrons more than hydrogen will, which means in this bond, electrons will shift to sulfur more than they will to hydrogen. Okay? So we can tell here that since sulfur is way closer to fluorine than hydrogen is, it's going to be a polar covalent bond. Okay, what questions? Let's try one now between sulfur and chlorine. So we determine electronegativity values for each of those elements individually. Sulfur we just saw was 2.58. Chlorine is what? 3.16. Okay, so we take bigger minus smaller. 3.16 minus 2.58, and we get what? 0.58. Okay, so what type of bond is it? Polar covalent. Okay, sulfur and chlorine are both nonmetals, so it makes sense that it's a covalent. Chlorine is closer, so the electrons will shade towards chlorine's side in this bond. All right, does that part make sense? Mm-hmm. So let's try one between hydrogen and hydrogen. Okay, let's make an H2 molecule. That's what it is. H2 is a molecule. Hydrogen and hydrogen bonded together. So in that bond that holds them together, what type of bond will it be?
Non-polar.
Yeah. Non-polar covalent. And do you have to do the math for it? No. It's 0. It's the same molecule. So this, if we're looking at a bond between two of the same molecule or the same atom, they're obviously going to want the electrons just as bad as the other one, right? It's the same element. Yeah, it's going to be nonpolar. Because they're all going to be pulling electrons at the same magnitude in equal directions. All right. We're going to look more specifically here at covalent bonding. What happens in covalent bonds? What do they do? What do electrons do in covalent bonds? Yeah, they share. Sharing electrons. Okay, ionic and covalent bonds is one of those big topics that you're just going to have to know. Okay, and as you go on in chemistry, you have to know that covalent means share, ionic means trade, kind of, or give away. All right, covalent means share. So we're going to look at sharing electrons and what are elements' goals when they share electrons. Okay, and their goals when they bond with other electrons is to complete what we call the octet. Okay. What do you think the octet means? Yeah, exactly. They want to have 8 valence electrons. They want to follow what we call the octet rule. Okay, and here's the octet rule. It says each atom wants to share electrons so that both atoms contain a total of 8 valence electrons, or 8 electrons in their outer shell. Okay, so that's the goal when covalent bonds happen, is that they want to fulfill octets of another atom, or they want to fulfill their own octet first and foremost. Then they want to bond with someone that will have a fulfilled octet. Okay? So you've got to start thinking in terms of 8 electrons. I want 8 electrons every time we bond. All right? We're going to look at how to find these, how to build them, how to draw them, all with following the octet rule. Okay. So covalent molecules or covalent bonds are only dealing with valence electrons. And where do valence electrons, or where are they located? Outer shell. Okay, valence electrons are outer shell. Valence electrons are located in the outer shell. And that's what we're going to start focusing on exclusively in these bonds, is that only outer shell electrons. So how many valence electrons does calcium have? 2. Okay, it has how many total electrons? How many total electrons does calcium have? 20. But we don't care about the other 18 in the first shells. We care about the 2 that are in the outer shell that are available to bond. All right, we don't care about the 18 in shells 1, 2, and 3. We care about the 4th shell, which contains 2 electrons. Okay, so that's important to remember. Just valence electrons. So when we're looking at individual elements and starting to diagram these individual elements, we're going to draw what we call our electron dot notations. Okay, and you can see what electron dot notations look like on page 184. If you look at the table on figure 10 on page 184, you can look at electron dot notations. And what they are is a representation of a single element and its valence electrons. Okay, so we're going to see how many valence electrons carbon has. Okay, how many valence electrons can you tell me from the periodic table that carbon has? 4. It has 4, right? Carbon has 4 valence electrons because it's in group 1, 2, 3, 4. So take a look at carbon's electron dot structure. It looks like this. There's 4 valence electrons around the outside. Okay, we kind of go around in a circle here drawing our electron dot structure. If we draw nitrogen, which has 1 more electron, we'll go 1, 2, 3, 4, 5. Okay. If we draw fluorine, which has 7, we'll go 1, 2, 3, 4, 5, 6, 7. Oops, that last one's kind of ugly. 7. Okay? We want to put them in pairs if we can. We have to go around first. So these are what we call electron dot notations. We don't care about the inner shells that are full. We only care about valence electrons. Okay, so we're just looking at outer shell. Yeah, Carson.
What about like hydrogen?
Hydrogens would look like this. That's it. And here's the thing. You can start, like for hydrogen or carbon or any of these that we start, you could start by drawing the dot on any side. It doesn't make a difference. You don't always have to draw it on the top. That doesn't make a difference. You want to kind of spread them as evenly as you can is the rule of thumb for these electron dot notations. So if I draw, let's see, the one that has 2, if I draw magnesium, I don't want to put them right here because they're too close together. I want to spread them as far as I can, so I put them opposite. Okay? Does that part make sense? We want to spread them out because electrons repel each other, right? If they're both negative charges, they don't want to sit right next to each other. They want to be spread out as much as they can. We're going to start combining them to form an F2 molecule. Okay, in an F2 molecule, what's that mean we have? Two fluorine atoms that are bonded together. Okay, so I'm going to draw the first fluorine here in black, and we'll draw its electron dot notation. So we're going to go 1, 2, 3, 4, 5. I'm going to go back here, 6 and 7. Okay, and you'll see why I leave this little dot to the right here in just a second. That's our first electron, or our first electron dot notation for fluorine, and our second one will be in red here. We'll go 1, 2, 3, 4, 5, 6, and 7. Okay, so these two fluorine molecules that we want to be, or these two fluorine atoms that we want to be bonded together, what do you think is going to happen with these two guys? They're going to share them. Oh, they complete each other. Okay, so when we share, right, you guys all learned when you were little to share. Okay, so we're going to try, I'm going to try and move this over here. We'll see if it works. Okay, so we're going to share those into one single bond. So now when we count to see if they fulfill an octet, we count each individual electron here. This black fluorine atom has 1, 2, 3, 4, 5, 6, 7 of its own electrons, right? Its own valence electrons, plus it gets to count this one that it shared from the red fluorine. Okay, same on this side. It has 2, 4, 6, 7 of its own electrons, and it's sharing one from this other guy, so it's got 8, and it's fulfilled its octet. And they're both happy, and this is a great molecule. Okay, and that's it. Okay, so this is electron dot notation. That's what it's called, electron dot notation. Not super exciting, not my favorite way to display things. We're going to move into a better way here called Lewis structures in just a second. But does everyone understand that these electrons get to count for both atoms when they are shared? Both atoms get to count those as part of their now outer shell. Make sense? So they both fulfilled their octet. Okay, great. Let's look at now something called a Lewis structure. Lewis structures are very similar to electron dot notations, except they are for compounds, not necessarily for individual atoms. So the way that we change this electron dot notation to become a Lewis structure is we take away our 2 electrons bonded here in the middle, and we make it a line. Okay? So this line, this bond, this right here, this line, which is a bond, equals 2 electrons. Okay, so for every line right here that bonds 2 atoms, you know it contains 2 electrons. So yeah.
So do you put it like all the way around? Like
You mean like right here?
Yeah.
Nope, because it's not bonded to anything right here. These electrons are still hanging out by themselves.
Oh, okay.
The only thing that's bonding is right here, because they're sharing. Okay, so when we count to see if we fulfill the octet again, we still count 2, 4, 6, 8 for this black fluorine, and 2, 4, 6, 8 for this red fluorine as well. Okay, so the bond means that they're bonded together at that point, and they're sharing those 2 electrons. Okay, what these guys are called, these electrons that are hanging out and they're not bonding, these are all called lone pairs. Okay, they're all alone, and they're pairs of electrons that want to bond with someone, but no one wants them. Okay? Yeah, they're sad. Okay, so these are kind of our steps for our Lewis structures. I'm just going to abbreviate LS, Lewis structures. Okay, the first thing that we do is determine total number of valence electrons for the molecule. Okay, so if we have the molecule NH3, what's our total number of valence electrons here? Nitrogen has how many valence electrons? 5. Hydrogen has 1 valence electron, and we have 3 of them, so it's 3. So right here, we need to have 8 valence electrons in that molecule that we'd have to represent somewhere in our Lewis structure. That's our first step, okay? And we're going to do a lot of practice with this. I just wanted to give you a quick example. Okay, can I get rid of this? NH3? Okay. Our second step here, we're going to arrange our atoms in what we call the skeleton. Okay, we're going to arrange them in what we call the skeleton. And here's our rules for arranging the skeleton. What the skeleton is it's the atoms without any electrons put on the diagram at all. Okay, so our 2 F's sitting beside each other would have been our skeleton on that last one. Okay, so a skeleton is the atoms in a particular order with no electrons drawn in yet. Okay, and here's our rules for picking a skeleton or what it would look like. Okay, if you have carbon in your molecule at all, it always gets to be in the center. Okay, so carbon will be central atom. Okay, if you don't have carbon, then the least electronegative atom gets to be the central. Okay, if you don't have carbon, then the least electronegative atom gets to be in the center. And I promise this will make more sense when we start working through them. Okay, I want you to see the rules first, and then we'll go. Okay, our last little section for this rule is that hydrogen can never be a central atom. Sorry, I know that last word's covered up, central. Okay, hydrogen can never be a central atom. Why do you think that is? Yeah, it only has 1 valence electron. Is that what you're going to say, Carson? It only has 1 valence electron, so we can only ever bond with one thing. Why would you want to put that in the middle if you can only ever bond it with one thing? No, it doesn't work. Okay, hydrogens go on the outside. Hydrogens always go on the outside. Okay? All right, next. Our third step here is to bond the central atom with each outside atom. So bond the central atom with each other atom. Oops. So after we draw our skeleton, we determine which one's our central atom. We draw a bond to each of those other atoms. Okay, then we fill with electrons to complete. Fill with electrons to the total number that we were supposed to have. Remember how we found our sum of valence electrons, that we have a total number of electrons we need to represent in our diagram? Then we have to fill it with our electrons around the outside, like we did with fluorine. Or we could add more bonds. We could have things like double bonds or triple bonds between atoms, and that's where the puzzle part comes in. You have to determine, do I need another bond? Do I need to put more electrons on? Do I need to whatever? Okay, so it's a puzzle, but you know how to check your answer, and that's to make sure that the electrons match the sum of electrons you should have been representing. Okay? And then last but not least, we have to remember hydrogen only has 1 valence electron. That means it cannot have a lone pair, it cannot have more than one bond, it cannot be the central atom. Don't try and make hydrogen a superhero. Okay? Hydrogen just gets to be on the outside. Okay? Cannot have a lone pair, cannot have a double bond, cannot be the central atom. Those are like cardinal rules of Lewis structures. If you do that, I'll probably put a frowny face on your paper. Yeah, you don't want a frowny face. Okay? That's as good as I can do it. Okay? You don't want one on your paper. If you do one of those three things, I promise I'll do a frowny face. I might even put a big X through it. Yeah. Yeah. Okay. Yeah. And then I'll probably bring you in for detention. No, I'm just kidding. Just kidding. Okay. But now you probably won't do it, right? Hydrogen cannot be a central atom, cannot have a lone pair, cannot have a double bond. Okay. So let's just start drawing some valence or some Lewis structures. Okay? Let's start with NH3, like our original little mini example here. Okay? We want to draw a Lewis structure for NH3. First things first, we determine number of valence electrons we should be representing here. N has 5, hydrogen has 1, and there's 3 hydrogens, so we need to represent in our drawing here 8 valence electrons. Somewhere, somehow, we need to have 8 electrons in our Lewis structure. They can be in bonds, they can be in lone pairs, whatever, however you want to do it. They can be in here, okay? Let's see. Okay, so what should be our central atom here? Nitrogen. Good. Don't even say hydrogen. Nitrogen, okay? So when we distribute the hydrogens around it for our skeleton here, we distribute them just evenly. Okay, so we just kind of distribute them evenly surrounding there. That's our skeleton, okay? And later on in chapter 6, we're going to deal with what we call molecular geometry, and that's going to tell us what shape these molecules really take on in 3D. That will determine how we draw our Lewis structures a little bit more, but for right now, we're going to just do it evenly, okay? So we've made our skeleton. Now we're going to draw our bonds. I'll draw those in red. Okay, we bond to each of those atoms. We bond our central atom to each outside atom. So let's see here. We started with 8 electrons we needed to represent. We used how many here? 2. 2. 2 and 2. So we've used 6 electrons already. That means we have 2 left we need to put somewhere on our Lewis structure. Where could those go? What? Okay, on what atom? Yeah, on the N. Good. Right here. Okay, so now we need to then go back and check that our elements fulfilled their octets. Okay, so I guess that should be your last rule. If you want to go back on your rules for Lewis structure, your last rule should be check for octet rule. Okay, make sure you put that in there. Check for octet rule. So let's count nitrogen's electrons here. Okay, it has how many here? 2, 4, 6, 8. Let me have them. Thank you. Okay, so, oh, stop.
Settle, guys.
Okay, we're looking at this right here. How many? 2, 4, 6, 8. Okay, has nitrogen fulfilled its octet? Yes. Does hydrogen get to fulfill its octet? Hydrogen only has 1 electron. It can't have 8. Okay? Hydrogen doesn't get that. As long as we're here, we're happy. Okay, so also something else to point out is look at nitrogen. How many valence electrons does nitrogen have available to bond? How many valence electrons does nitrogen have? 5. Okay, it started with 5. Right here, it's sharing 1 in this bond. So 1, 2, 3. It's sharing 1 here, 4. It's sharing 1 here, which is 5. Okay, works out, right? Okay. Questions here? Okay, let's do another one. Okay, let's try here. H2S. H2S. Okay, a hydrogen has one valence electron, and we have two hydrogens, so that's going to be 2. Sulfur has how many valence electrons? 6, because it's in group 6. That means we need to represent 8 valence electrons. Okay, so what would our central atom be? Sulfur.
That was bad, Mary.
Sulfur. Okay, when we draw our skeleton, where do our hydrogens go? Yeah, we'll just put them on each side. Okay, it's not a huge deal right now. We'll learn geometry so that'll tell us where to put them, but that's all right for right now. Okay, so let's say that we've got our skeleton drawn. Now our next step is to bond our central atom to each outside atom. So thus far in our, I can't talk over you, I'm not going to do it. Okay, thus far in our Lewis structure, we've used how many electrons? 4. We've used 2 here and 2 here. That means we have 4 left to put somewhere. Yeah. Okay, so now sulfur has 2, 4, 6, 8 electrons surrounding it.
Why don't you put them like side and top?
Yeah, you could do that. It doesn't really make a difference. We're going to look at 3D shapes, and really this molecule should look like this. Okay, this is what's called bent geometry, and that's what it should look like. But for right now, our basics is here, and that's okay. Okay? It's just what it's called. It doesn't really have anything to do with geometry. It's just the 3D shape of it. It's no big deal. All right, let's try another one. First of all, tell me the name of this molecule. Phosphorus trifluoride. Phosphorus trifluoride. Okay, so tell me how many valence electrons phosphorus has? Fluorine has how many? 7 times 3, which is 21. So we have 26 valence electrons we have to represent here. 26. A little bigger than normal, right? Okay. So which of these should be our central atom? Yeah, phosphorus. It's less electronegative. We don't have carbon. We don't have hydrogen. So now we need to look at our least electronegative. That's phosphorus. How is it less electronegative than fluorine? Fluorine's the most electronegative element that we have. And look on that scale. Yeah, that'll do it. Yeah.
Oh my gosh.
Yeah, that's it. Okay, so now we're going to space our fluorines out evenly. And we'll draw our bonds from our central atom to our outside atoms. So we've taken away 6 electrons. We have 20 left to put in. Okay, so let's think about this right here. Does fluorine have a completed octet, a fulfilled octet? How many electrons does fluorine have right now?
Yes. 8, yeah.
2. It only has 2 because we can count these for both. These get counted for both atoms. So right now it only has 2 electrons. What do we do?
6 more.
Yeah, we just add 6 more. Of course, obviously. 1, 2, 3, 4, 5, 6. So we've just used 6 more of our electrons. We have 14 left to put on. So what do we do now? Put them where? Next fluorine. So we'll go 1, 2, 3, 4, 5, 6. We use 6 there. We have 8 left. We'll go to our last fluorine, do the same thing. 3, 4, 5, 6. We take away 6. We still have 2 electrons left to put somewhere. Yeah, put them on phosphorus.
I didn't know to add 6 more.
To the fluorines to complete their octet. So now fluorine has 2, 4, 6, and 8 electrons around it. Now this fluorine has 2, 4, 6, 8. This one has 2, 4, 6, 8. This phosphorus has 2, 4, 6, and 8. Yes, Brent.
Does phosphorus always have to have
electrons, like it has 2 right now, does it always have to have just one?
Does it always have to have one lone pair?
No, I mean, if you would have had 18 instead of 20, because you still distributed 6 dollars and no extra.
Oh, no. It's got to fulfill its octet. Okay, so there's some, well, if you have PF3, then it wouldn't have given you 18. You know what I'm saying? I know what you mean. There's some exceptions to the rule, like boron is an exception to the rule, sulfur is an exception. There's some that are, and we'll go over those just very briefly. Okay. All right, let's try one that's a little trickier. Okay, now we have 3 elements that we're looking to. So let's take our valence electrons. Carbon has 4. There's 2 hydrogen there. Oxygen has 6. So we have 12. Okay, 12 valence electrons. So this is, I'm gonna give you a little clue here. The way this is written gives you a clue to the Lewis structure. Okay, so CH2 means that these 2 hydrogens are bonded to that carbon. The oxygen is then also bonded to that carbon. Okay, so the H's that are in the middle like this are bonded to the preceding element. Okay, or preceding elements. So they will look something like this. Actually I'll just do the skeleton. CO, H, and you could put the H down here, or you could put it over here. This is probably a better way, like this. Yeah.
What if it was
It wouldn't be, but if it was, it would look like this. CO, H, H, but that doesn't happen that often. But yeah, that's what it would look like.
I don't understand.
Okay, what do you have a question about?
Like, how do you know how to write it like that?
This CH2, this H2 right here is telling us that it's bonded to those carbons.
Yeah.
Okay, so then the oxygen is also bonded to that carbon because it's got to be bonded to something, right?
Yeah.
And carbon is less electronegative than oxygen, so it gets to be in the center.
So it has to be written with the H's like that.
You could write it like down here instead.
So it doesn't matter.
Doesn't really matter. Again, once we get into the shapes, then we'll determine what exact representation we have to have. But for right now, we're just learning basics, not really worried about it.
All right.
Okay? All right, so let's draw our bonds. Here, here, and here. So far we've used how many electrons? 6. So we have 6 left over. What do you think we do? Let's fill oxygens. So we just used 6. So let's take a look here. Does carbon have 2? Oops. Carbon has how many electrons around it?
6.
Is that filling its octet? No. So that doesn't work.
Take some off.
Okay, so if we take these off oxygen and put them here, carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6. Shoot. What do we do? Yeah, so what we're going to do is we're going to take these electrons here and we're going to move them up to make a double bond right here. Oh, okay. So now we're going to go like this. And then we have 2, 4, 6, 8 around carbon because each of those bonds contains 2 electrons. And then oxygen has 2, 4, 6, and 8. And when we make our double bond, we need to then move these lone pairs around so they're kind of evenly spaced and they look like this. Okay? I just moved the double bonds, shifted them around, or the lone pairs around so they looked a little bit nicer. Okay, so after you fill the electrons around the outside, if you are short or you don't have enough or something doesn't work around the outside, you need to then look at adding double bonds or rearranging or something like that. Okay?